Welcome to my new tutorial where we will implement a Mure machine. So basically what we are going to do in this tutorial is that we will implement this particular Mure machine um, using behavioral modeling. So, uh, so, so let's begin with that. First we need to add a source. So I've already made this project. So now we are just going to add a file, a Verilog source. So select this Verilog module here and then write the name. So let's call it Mure mod. Click next, next and finish. Okay, so using this input command now just uh, define that X CLK, that is clock, and RST, that is reset, are inputs, and Y is our output. Let's now use this reg command to specify state variable. So basically we have two states here, so let it be a 2-bit variable. Okay, so now so as we know, in behavioral modeling we do not implement the actual circuit, we implement the behavior. So behavior of a sequential circuit is defined by the state machine. So let's go to the state machine of this circuit. uh, right, this is the state machine that we want to implement. It is a Mure model, as you can see here. Right. So we are going to implement this Mure state machine. So first we have four states here, as you can see here. So let us define uh, these parameters. S0 as states. So instead of so we'll use these parameters as our state symbols instead of using 0 0 0 1 1 0 and 1 1. We assign these states to these parameters, and then we will use these parameters as our identifiers. So S1 is equal to 2, B0 1. Right. Okay, so this is how we define parameters, or you could also call them identifiers. So basically these are constants, right? So this S0 is a constant that represents 0 0, S1 is a constant that represents 0 1, S2 is a constant that represents 1 0, and in fact S3 is a constant that represents 1 1, right? Okay, so now let's uh, use the always block. And in sequential circuits we use CLK as our execution condition. So the CLK and RST. So we generally use the positive edge of the clock and negative edge of the reset. Okay, so we want to say that F, let's use this begin block statement. So we say that if RST is equal to 0, right, and then in that case state should be 0. So this is our reset condition. There should be no change in the states if RST is 0. So right, and now we specify else. Maybe we can bring it here, and then we can specify else, and inside else we need to implement this state machine. So now to implement this state machine we use case statement. So let's use this case statement, and the input to this case statement should be the state, and it has so there should be this end case at the end of this case statement. So let's write it syntax first and now specify the cases, right? So it has basically it has 4 cases. All like all the 4 states make 4 cases, like so, right? So S0 first case. So first write these cases here: S1, S2, S3. So now we need to specify what should happen if this particular situation rises, because so now when state is S0, so in that case what should happen, we should look here. So when state is S0 and input is 0, so the next state should be S1, and when state is S0 and input is 1, so the next state should be S0 itself, right? So if input in this case is X, so if X is equal to, you could also write it like this, if X is equal to 1, but um, so in this case, since X is a 1 variable or 1 bit digit, or sorry, 1 bit input variable, so in that case it could only have 2 possibilities, either 0 or 1. So there is no need to write this, because whenever the X is going to be 1, automatically this if statement is going to be true. So now you need to specify what should happen if X is equal to 1. So if X is equal to 1 and this if statement is true, so we want the next state to be S0 itself. So we write that state should be equal to S0. And now in else we want so the else should will be the otherwise case, the case of input 0, right? So because in this case this if statement is only going to be true if X is equal to 1, so it is going to be false when X is equal to 0. So it means this else represents X is equal to 0. So we need to write this state should be equal to S1 in case input is equal to 0, that is else in this case. So now we need to copy this, so it's very easy to implement the rest of the cases. Right, so now when we are at state S1, if input is 1, next state should be S2. So if input is 1, next state should be S2, right? And if input is 0, next state should be S3. Right. Okay, so we copy again here. So in case of the state S2, if input is 1, the next state should be S2. So we are at S2, and in case of input 1, next state should also be S2. So it should retain its state at input 1. And in case input 0, the next state should be S3. So here we are. And now we implement the final case. And so when we are at this state S3 and input is 1, we would like to stay here, because in this case it retains its state at input 1, and in case of input 0 it goes back to the reset state S0. So that's it, we have implemented it. Now we need to specify that the output Y is equal to the state variable, right? So in order to do that, we need to define output as reg type, and we need to specify that it has 2 bits, right? Because that's why we are doing that, because in this case, if you go back and see here, it has basically the output of the flip-flops are the actual output of the system. So basically the output vector is also has 2 bits. So the states are the output. So we need to specify this here, right? So once we have done this, fact, so now we have implemented this Murray model. Now it's time to simulate it. So let's save it and click on the simulation and see if there are any errors or not. So click on this ISIM simulator, click on the behavioral check, and yes, there are no errors apparently. So we add a new source, and we want to make a test bench. So click Verilog test fixture, write tb underscore Murray underscore model, and now click next. Select this Murray model here, click finish. So now we are ready to make this test bench. So uh, so now we assign some uh, inputs and outputs. Sorry, some inputs to see the outputs. So first we make this clock circuitry first. So let's make it always and specify that the clock should switch after every 5 nanoseconds. So maybe let's uh, so we do that by just equating the clock with uh, its complemented version, right? So now we have generated this clock. Now we need to go here. So now we need to specify input combinations. So let's copy this from here, and what we want to do here is to uh, change inputs repeatedly. So let's maybe let's keep x is equal to 1, and then 0, and then maybe 1 0 again, and 0 here, uh, and let's make 1 here, right? So this is the input combinations that we want to give, and let's add some more values here. And now we make it 0, right? Okay, so now maybe let's change this timing, the delay time. Maybe let's make it 15, make it say 20, and let's 5. Let's give a delay of 5, and then so you could choose delay timings differently, or you could keep them uniform. But since we are using clock and it is changing uh, values after every 5 nanoseconds, so it's good to change the delays so that you get a better idea of the output. Right. Maybe we can delete this. So that's it. So we have made this clock, and we have assigned these input combinations. We have also set the reset equals to 1. So let's run its behavioral model. Yes, it's working fine, and now let's simulate this as well. And now let's click on the simulation. right. So maybe there is some issue. We need to maybe rerun this. So it's always better to go back and maybe rerun all, and again come here, again rerun all, and then click on this. Right. So so since I use this finish command, so it has, so it basically means that the simulation is finished after 146 nanoseconds. So this means now we need to click on this default, and so here is our simulation. So now let's click on this screen to fit, and as you can see, so this is the clock, which is changing after every 5 nanoseconds, and so this is the reset, and as long as the reset is 0, output is 0, as you can see here. But when reset becomes 1, as you can see, the based on different inputs, the output starts to change, right? So this is how we implement a Moore machine. Thank you very much.